Hello, good morning, good afternoon, and good evening for everyone who's tuning in. On behalf of PioPetro and Military Research Hub, I'd like to welcome you all in our summer internship program. My name is Mayar Tare, a senior gas and petrochemicals engineering student, SB Egypt Young Professionals member, and I'll be your moderator for today. So, before we start, please keep the chat box professional and ethical, and don't forget to drop your questions in the Q&A section below. So, without further ado, let's welcome Dr. Mohamed Ghareeb, who will give us a session on artificial lift technology. Dr. Mohamed has PhD in petroleum production engineering with specialty in artificial lift and production engineering and operation. He is currently a staff member of Future University and a head of petroleum technology department of New Cairo Technological University. Meanwhile, Dr. Mohamed is Global Technical Director of Artificial Lift System for United Lift Technologies. Dr. Mohamed is a technical and business professional with over 34 years experience in oil and gas industry, with long experience of business development, sales, marketing, operation, teaching and applications engineering covering artificial lift design, operation, troubleshooting, and optimization for major services companies like Lufkin, GE, Tundra, Process Solution, Weatherford, United Lift Technologies, and oil field operation for major operator like ENI, Agiba, GPC. Dr. Mohammed field experience include the setup, installation, operation, and optimization of different forms of artificial lift systems in the Middle East, North Africa, Russia, Romania, Turkey, and Brunei. Over the past years, Dr. Mohammed also has played a major role in the practical training for the field staff and engineers in the oil and gas production engineering and well operation for different major companies in the MENA region, USA, Canada, Romania, Turkey, and Far East. Dr. Mohammed was Society of Petroleum Engineering SPE Egyptian Section President Program and Membership Chairperson. Also, he is the membership chairperson and director of SPE International Artificial Lift and Gas Well Deliquification Technical Section. Dr. Mohammed published and presented over 55 technical papers. He chairs several technical sessions for the local and international conferences and workshops. Currently, he is a committee member of ATCE 2020 and 2021 MEALF SPE Middle East Artificial Lift Conference. Dr. Mohamed Ghareeb is 2011 and 2020 recipient of the SPE Regional Technical Award in Production and Operation. Thank you so much, Dr. Mohamed, for coming today, and the mic is yours.
Thank you, Mayar. Thanks as usual. Thank you. Assalamu alaikum. Good morning, good afternoon, good evening. Will I just to continue starting? Sorry for what happened yesterday about the power and so on and disconnected. Today we'll try just to continue from what we are stopping yesterday about one of the major form of artificial lift. We said just yesterday we plan to cover most of artificial lift system, most form of artificial lift system. Yesterday we covered the first 2.1 and 2, and today we plan to going to cover some basic informations, general information about the gas lift, while if you are aware of this one or know this one, you can able just to understand very well the gas lift and so on. Gas lift currently, as I said before, they start to be one of the major artificial lift after that application of unconventional fields and so on, especially deep field, high gas or ratio wells and so on. Artificial lift start to be one of the most economical gas lift, one of the most economic artificial lift for this type of field and so on. Then yesterday we said that just the gas lift. What is the gas lift and how it's working? The gas lift, how you start to thinking about gas lift. When you start to think about gas lift is one of the major, as I said, one of the major artificial lift forum. Especially for a certain application, certain area. If the gas lift is working for the well, it can be most of the economical artificial lift. Its gas lift is, you can consider it is a extension of a flowing wells. If you look to the gas lift, it's behaved like a gas well, like a flowing wells, but with some artificially, interference from your side, for that wells to keep the well flowing. Yesterday, we said that in order the well to be flowing, you must have the bottom hole pressures capable to lift the hydrostatic head of the fluid inside the tubing, inside the well, up to the surface. Plus, to overcome, the wellhead pressure, we need certain value of wellhead pressure for the fluid to move from the wellhead to the inside facilities, whatever facility you have. Is in some areas the facility is far, and there is a plenty of oil in the fields, and the outlet pressures can be reached to more than 300, 400 psi. Then you need to have that value. Plus all the pressure loss. You have downhole from bottom to the surface and so on. Then if you are overcome these three items, then the well can be flow. But in this case, will be flow artificially by using naturally gas. Use gas compressed, and you are pumping you are compressed the gas. Compress the gas from the surface at the surface inside the annulus, and this gas, through a certain valves. We'll plan to explain what this valve. It's jointed the produced fluid, inside the tubing, and help or support the wells to be flowing and just produce the required production to the surface. What type of gas is used for the gas lift system? In general, and majority of the wells is used natural gas. Natural gas either is from the produced gas from this well or some other wells, or if you have a gas field near of you, you can use it. And even sometimes if the wellhead pressure of the gas field near of you, maybe you don't need some compressors at the surface. Plus, sometimes you can have some air for very shallow wells. Some wells in some area. It's not a common, but it can be. The main idea here to have some sort of gas in just mix it with the fluids in order just to help the well to flow to the surface, and can be a mixtures of gas, air and gas. But however, let us to focus on the first one. It's using the produced gas or natural gas, what we can found. This is one of the main important, thinking about how to use a gas lift and so on. In general, there is more than one type of gas lift. Yes, depend on the well, depend on productivity, depend on the bottom hole pressures, depend on how you want to produce these wells, what is the bottom hole pressures, what's the amount of fluids you have in the well, and so on. In the market, generally speaking, there is what we call first continuous flow gas lift. You are continuously compressed gas, continuously injected gas in the well. In the other also, we have what we call intermittent flow gas well. You are injecting gas, stop, injecting gas, stop, and so on. How this type of just technique or methods is working, I will just talk you through this one. Then we have two types of system of gas lift. It's what we call continuous flow gas lift and intermediate flow gas lift. What is a continuous flow gas lift? How the conventional gas lift, the continuous flow gas lift is working, how a gas lift system it works. For the conventional gas lift, what we call continuous gas lift, and so usually, and also the other type of gas lift, but in the first one, the continuous flow, or just the other one, you are injecting gas from the casing. There is some case, but it's not in our focus today. Sometimes some people injecting from tubing. This is different subject now, but let us to focus on the principle. You are injecting gas. This is the yellow arrow in the annulus space between the casing and the tubing, and the gas is entered to the tubing through one of valves. I will explain you how valves through a certain port, and jointed the produced the fluids and lifted the fluid to the surface. like this, If you look to this one, this is just animations about if one of this, usually in gas lift, only one valves open at time, even if you have more than one valve in the well, but only one valve is open at the time. The valve is open, it's called operating valve. For this one, if you are injecting gas in the annulus and the gas just go to the tubing through this port or this valve, jointed the fluid of the tubing, and this is, reducing the hydrostatic head. One of the main purposes of that, reducing hydrostatic head. And also there is some other techniques here I will explain later on, for the gas lift, how to lift the fluid, and just, is lifted the fluid and produce. Then continuous flow, this is a continuous flow gas lift. How it's working, again, how it's working in the continuous flow gas lift. Principle, we said that we're injecting gas through the annulus. The gas is entered to the tubing through the valve, the bottom valve, this one, and jointing the tubing to the surface. How is working? How is simulated this one, How is lifted fluid? Is only by reducing the fluid gravity, the density, the average gradients of the fluid, or what we have. This jointed gas, joins the formation gas or formation fluids, the produced fluid to lift fluid to the surface. Usually there is one or more than process just helping the fluids to flow from bottom to the surface. What is this process? First, always thinking about, and this is the main also idea, and the main concept in the gas lift is reducing of fluid density. I have a fluid inside the wells, or for example, water, oil, whatever, gravity of the oil. If it is dead oil with API, for example, 40, then the average gradient will be how much? About 0.3 psi per foot. If I injecting some gas and the gas mixed with the fluid, then the average gradient for sure will be less than 0.3 psi per foot. Then the hydrostatic head equivalent to the well depth will be much less. This is one of the main process. What else? Yes, in the same wells, especially if you have high gas ratio wells, deep wells, and so on, this gas, when it start to travel upward, look to that one, the bubble of gas start to be expanded. When the bubble of gas expanded, expansion of the injecting gas, so that it push the fluid, push the liquid ahead to up. Usually the gas is moving up, is not moving down, Then when the bubbles of gas start to be expanded, it's pushing the liquid or the fluid up further to reduce the column weights more and more, helping fluids to move up and so. If there is some other technique or some other possible process, yes. Not only that, the gas, as much as going up, the pressure decrease, and when the pressure decreases, the bubble of gas or slug of gas, it start to be expanded, start to be bigger and bigger, and so on. And when we have a slug of gas, big slugging of gas inside the tubing, this slug of gas making displacement, all the fluid above of it, then displacement of fluid used by the slugging. In the same wells, you can find one of these processes or more than one of these processes. For sure, the first one is okay, you can find just this is only bubble flow reducing the density of the fluid. Bubble flow with expansion of gas. If the gas start to move up and up with a certain velocity and start to be, slugging, then you can have more and more processes. Usually, you want to start to design the gas lift and start to look to what's happened downhole for two-phase flow, because usually gas lift, why you say it is an extension of the wall of the flowing wells, because usually you are dealing with two-phase vertical flow concept for these wells, Then when we start to design with the correlations, we know what process in the well, how we can move from one process to the other. If we wanted to have more than one process, two processes, then we can start, to control amount of gas and pressure of gas going to the wells and injecting to the wells and so on. This is a continuous flow gas lift. We said that in gas lift techniques, there is two techniques, continuous flow, and the second one is intermediate flow. The continuous flow, the one is using for high production well. For well producing continuously for the well with a good productivity and so on. What happens if I have a wells with low productivity? These wells, only producing, very low amount of fluids, and these fluids cannot be reached to the surface. But the well capable, the fluid inside the wells, it is, what you call it, as a fluid gravity, viscosity, and so on. The design said yes, gas lift can working in that case. In this case, what you have, well fluid is your well stopped, and then you allowed the well fluid to be accumulated at the end of the tubing. If you stop the well, there is technique what we call is the build up. The well start to be built up, building up what? Building up the fluid at the bottom, because the fluid is heavy, fluid at the bottom as a pre-designed amount of fluid, head of fluids will be in the well, then we know, okay, yes, when the fluid is built in the bottom of the well, for example, 100 feet, 200 feet, 300 feet, then I have to inject the gas in the annulus to push that fluid already accumulated in the well to the surface. When the fluid reached to the surface, this is like that, the well is stopped, no gas injected, and there is a fluid in the bottom of the well. When we have a certain amount of fluid in the bottom of the well, I start to inject the red arrow, here, gas inside the annulus, entering to a certain valve at the bottom. This gas is going to below the head of below the columns of the fluids, and pushing that fluids to the surface. Pushing that fluid to the surface until the fluid reached to the surface. There is valves there. Since the fluid reaches to the surface, then this well I stopped again. After I stopped the well again, and the cycle start to be repeated and repeated. Usually, this type of intermediate gas lifted use for low production well, for low productivity wells. And however, it's not an economics, it's not an efficiency, efficient, because in most cases you have a lot of fluid slipped back. Again, when you are pushing gas, it's not working like a plugging, it's a fluid. It's a fluid, then the gas can be, move through that flow. And it's not, very efficient and so on. Sometimes it's used for shallow wells, low productivity wells, when it was, the other form of artificial lift, maybe is not economical and so on. Sometimes it's combined with some other type of artificial lift, like plunger lift and so on, plunger assist. However, this is the second technique or second process of the gas lift system and so on. This is slide just explain to you, the process, how it's working, if you looked from the left side one, this is at the bottom, there is a fluid, just accumulated. If you look to the surface, what happened here, the well, immediately just before injecting gas, there is a fluid in the bottom. At that case, you have the surface control valve is closed. Then after I have a certain volume of the fluid inside the wells, what happened? The surface control valve start to be open and allow the gas to be injected inside the well. The gas go below the plug. After the gas go below the plug is pushed the plug to the surface. Second one is during the injection operations. When the slug is reached to the surface, in this case, there is a sensors at the surface. It say, okay, this is now all the plug or the end of the plug or the gas. The plug is moved, and from the wellhead and so on. The surface control start to be closed because the well completely now is filled with gas. Why are injecting more gas? Because only the fluid is reached, and at a certain depth, a certain well place in the wellhead, since there is no more fluid now, or the plug or the fluids start to move, and this only sensing gas. Then, when this close is allow the wells just to be stopped. This just after the injection, when the well is stopped, start the flow to build up again, and the cycle is repeated. This is what we call intermittent gas flow. Gas lift operation usually, how I use gas, from where I use gas, what is the source of my gas, how the field working with the gas lift is looks like, usually in all fields, if one ring with gas lift or any type of artificial lift, you have more than one wells, in the field, more than one well. All these wells is producing. When the well is producing fluid with gas, all the production of that wells going to the surface facility. From the surface facility is have a separations of the gas and the fluid. They are taking some of the required gas, required to inject based on my previous design, and this gas going to a compressors. The compressors is compressed the gas, and you have some, measuring control manifolds, to control amount of gas required for each well, amount of gas and pressure required for each well, and distributed. And the cycle repeated. This if you are using the produced gas. If you are using outsource of gas, then you have something different than this. You have source of gas, but meanwhile going to also the manifold measuring devices, control station, and the control amount of gas going to each wells, and so on. Okay, based on that, based on the gas lift, based on why I use gas lift, based on what I mentioned about gas lift, for sure there is some advantage, some limitation, and some disadvantage for gas lift. As I mentioned, the gas lift, it is an extension for the flowing wells. There is no moving parts. There is no moving equipment inside the wells. Then the gas lift can be handled, sand, handle, whatever, even can be used for deviated wells, for horizontal wells, for whatever type of wells. There is no restrictions, inside the wells for flow to move in the tubing, because there is no mechanical movement. Not only that, gas lift really, it's more flexible type of artificial lift for design rates. If I design the well, for example, for a certain rates, and based on well productivity, based on the amount of fluid, based on water cut increase, decreased, and so on, I can control the injecting volume and pressure of gas, and the place even, when I need to inject the gas, at what depths, at what valves of the depths. And then you can have more flexibility on gas lift. For that reason, one of the main important things for the gas lift is optimization. It really is one of the artificial lift required continuous optimization, continuous monitoring, what's going on downhole. Do I use a gas in my best efficiency, best economical ways, and so on, Since there is no, nothing inside the well, inside the tubing, only the valves, the gas lift valves, and so on, then the tubing have a full pour tubing draft. Then you can run whatever you have inside the tubing. You can do some wireline operations, some downhole perforation, some downhole cleaning, whatever you have. You have a tubing you have full pour from inside the tubing. Even the wellhead, if you look to the wellhead of the gas lift, is only Christmas tree. It's very small, similar. If you go to the well, if you not notice the casing and the line going to the casing, you saw that is a flowing wells. It's only have a Christmas tree in the well, at the wellhead, and so on. The equipment, the gas lift, or it's using what you call gas lift valve. This gas lift valve can be retrieved by wire line, is a slick line, what we call. You don't need a rig, no rig. For that reason, one of the main reason using gas lift in offshore operations, because it's not required rig in case any problem happened for the gas lift valves and in the downhole. You can use multi-well production from single compressor, as there's a previous slides what I mentioned. We have one compressor, and this compressor is compressed gas to different wells, maybe to, I don't know, depend on the amount of gas, the volume of compressor. Then from one source of compressors, you can run different well. For that reason, again, it's using as a platform. You have only one compressor, and one compressor run all the wells in the platforms, and so on. But meanwhile, no one of artificial lift have only advantage. All of them have some advantage, some disadvantage, some limitation. Limitation mean that I can use, but with a certain limitation, with a special design. We have to be monitoring closely the economics, the efficiency, and so on. This is type of artificial lift need high pressure gas well or compressor. you must have a compressor to compress the gas, or if you have a high pressure gas well near of this, then okay, you can run this. Usually one well is non-economical because the compressor, running compressors, it's really the operating cost is high and so on, Since it's using gas and gas simulated the wells and the gas injecting to the fluid and try to mix it with the fluid, then when the viscosity of the fluid increase, this is efficiency of that gas injection will not be high. The fluid will be slipped, the gas slipped and the fluid will be, will be a big difference in viscosity and so on. This is like a flowing wells depend on reducing hydrostatic head. Then any bottom hole flowing pressure change is sensitive. Because in this case, what I simulated, as I said, like a flowing wells, then flowing well depend on one bottom hole flow pressure to lift the flow to the surface. Then when bottom hole flow pressure is changed, decreased or increased, whatever, then the gas lift efficiency will be changed. Same here, the back pressure, the wellhead pressures, we said that the bottom hole flow pressure must be equal the hydrostatic head plus the wellhead pressure plus the pressure loss. Then when wellhead pressure is increased, that means the volume of gas I need to inject, or just the place of gas I need to inject, it can be, should be, redesigned or just reevaluated and so on. And maybe sometimes it's not economical, or sometimes you're not able to lift all the flow. Then the back pressure is so sensitive. When you have the back pressure, suddenly, immediately you have low production. Any operations in the surface facility, in the pipeline, it's creating some back pressure, increasing the wellhead pressure, you will notice that the well production or production from this well will be decreased. What is the equipment used for gas lift? What type of equipment usually I use to gas lift the well? Since I said, I run this well with artificial lift, then it must be a certain equipment used to artificially lift that wells. And all type of artificial lift, when you start to say equipment used to artificially lift that wells, that's mean we have a surface equipment and downhole equipment. For gas lift, what equipment we have? This is just, show you these slides, simulate what the gas lift was, what we have in the bottom of the well, what we have in the surface of the well. For the gas lift, component, what component I have? What is the downhole component? Downhole, that's mean all the equipment in the well, below the wellheads, down to the wells. Whatever I found in the wells, we call downhole equipment. What's the downhole equipment for gas lifted wells? Mainly, we have gas lift valves. Some valves, because, I injected gas, but, I need to have some control for the gas is injected. Where I need to inject the gas? I need to inject the gas as a depth of 1,000 feet or 2,000 feet or 3,000 feet or whatever. Then at what depth I need to inject the gas? How volume I need to inject the gas? Then I need to have something sort of control, something to control the amount and the place of gas to injecting downhole the wells. This is what we call gas lift valve. How the gas lift valve will be installed inside the well? The gas lift valve, like this picture, just a piece of equipment. It's very small and so on, How you fix it inside the well, because this must be fixed inside the well. And meanwhile, must be allow the fluids, the gas to communicate it. The fluid to communicate it, there some sort of communication between the fluid in the annulus and the fluid in the tubing. Then this gas lift valve is installed in what we call gas lift mandrel. Even mandrel, gas lift mandrel, it is a place in which the valve is placed. This is a gas lift valve, and this is a gas lift valve inside the mandrel, and this is the mandrel. Usually the mandrel is a part of the well completions. When you run the wells, and you have a mandrel with threaded in the top and the bottom, and you are connecting to the tubing at a certain predetermined depths or predetermined places, and you connect it. After you run, and you can run the wire line using wire line, you run the wire line, you run the valves or just after that you can retrieve the valve. This will be, how the valve installed inside the mandrel. Then in the downhole, this is a mainly, there's some type, some accessories I can use sometimes in such type of oils and so on. In this is a gas lift equipment. I am not talking about completion now. I'm talking about the gas lift equipment and so on. In this case, if you look to the gas lift valves with the gas lift mandrel, this is one, the red colors, this is the gas, and this is the gas lift valve, and this is the gas lift mandrel, just zooming on that one. When at a certain delta P pressures between the tubing and the casing, the valve is open, allow the gas to enter to the tubing, and when enter to the tubing, make fluid, and lifting was one of the processes what I mentioned before. At the surface, remember we said I must have a control. I must have something to control the well is open or stop, volume of gas, pressure of gas injecting, and so on. Then I need to have a compressors or high pressure line. Compressor or high pressure line usually is not for one well. Compressor sometimes, for in most time, for couple of wells or more than one. But however, I need to have a source of high pressure gas. High pressure gas come from a line, from a wells, from compressors, and so something, to compress the gas and to just give me a gas at the wellhead with a certain value of pressures over this gas. Plus, the wellhead for gas lift is very simple. It's just a Christmas tree and so on, plus a control valves or control whatever, just to control flow and control pressures and so on. Then let us to focus a little bit more about valves, gas lift valves and gas lift mandrels and so on, and why we need gas lift valve. Someone will say, okay, why we need gas lift valve? This is a cross section, on the mandrel and the valve installed inside the mandrel. Then the gas lift valve, we are needed gas lift valve to provide the communications, some communication for the fluids between the fluid in the annulus and the fluid in the tubing. I have to communicate, between the fluid in the annulus and the fluid in the tubing, with the controls, when it's open, when it's closed, when I need to have the communication, when I need not to have a communication, like isolated, like stop this one. Then the valve is to control the flow of the injected gas into the production tubing. Then I need to inject gas in this case, or I need to stop. I need to inject the gas at that depth or not, or depths deeper or just shallowers and so on. Then the valve operation in this case, it's depend on a preset opening. Since the valve is controlled, then I have to preset the valve. Preset the valve, what that mean? The valve in the workshop, just to set that valve, I say, okay, this valve with a certain techniques, I will show you later on, certain techniques, this valve should be, if the pressures in the annulus is higher than the pressure in the tubing with a certain value, the valve should be open. If the pressure is low, the valve should be closed. If the pressure higher more and more in a certain thing, the valve should be open or closed. And then the valve open or close, it's based on a preset the valve in the workshop. We say, okay, if you have a delta B across you from the casing and the tubing, you need to open or you need to close, Then in this case, the valve operation depends on preset opening and closing pressure in either tubing or casing. He sends with the delta B from casing to tubing or from tubing to casing. There's different valves and different technique of valve using for this. Then each one is looking for the gas lift wells or gas lift completion. You will find more than one valve in the well. The well maybe have 5 valves, 6 valves, 10, 15, small, then I have more than one valves in the well. Why I use more than one valves inside the wells, More than one valve inside the wells. Is this all the valves working? Is this all the valves working at the same times? Or what is the reason using these valves? Usually, all the valves in the wells, inside the wells, it should be only at the times when I have operation, only one valve should be open and the rest of the valve will be closed at the same time. When one valve is open, the other valve immediately it should be controlled. Based on what? Based on the preset pressures for the valve in the workshop. All the valve inside the wells have some name, certain names in them. All the valve inside the wells above the operating valve, that means the valve I continuously operating to inject gas, and this valve is open and allows the gas to go inside the tubing. All the valve above this valve is called unloading valves. Then, what is unloading valve? The bottom one is called operating valve or orifice valve. Some people know it's orifice valves and so on. But all the valve above that is called unloading valve. What mean of unloading? Why I need to do this unloading or unloading valve? As I mentioned before, according to the gas lift valve design, all the valve will be closed until a certain condition of pressures across that valve between annulus and the tubing is met or reached. When the valve is open, it's allow the gas or permit the gas to pass from the casing to the tubing and mix it with this one. An operating gas lift valve is installed, as I said before, to control, the injection point. When I need to inject in this point, or in this point, or in this point, or in this point, above or below, Okay, then the valve are installed above the desired valve or operating valve is used for unloading the wells. Let us to see what mean of unloading the wells and why I use it. Usually when the wells is die or just the well is stopped or after work over or have some shutdown operation and so on, what type of fluids will be inside the tubing? In this case, you will have inside the tubing only liquids. Because if the well is stopped, then the liquid is accumulated. You have a liquid inside the tube. If the well is producing and stopped due to any situation, any type of shutdown, any type of operation, then I have a liquid. After workover operation, what type of fluids you will have inside the tubing and the annulus? You have the killing fluids. You have the killing fluid. Usually, it's I don't know, water or KCl or diesel, whatever you have. Then the fluid. All the well will have only single phase, liquid phase fluid inside the well. If there is no unloading valve and I want to produce the well, in this case, if I want to inject gas, I need to inject the gas to a certain place. This gas, the gas pressure at the surface and until it's reached to the operating valve, these pressures, should be roughly equal hydrostatic head of all the fluid column inside the tubing. And usually the fluid column inside the tubing, especially if it's water, the hydrostatic head will be a very high. In this case, I need a very high pressures at the surface at the beginning. Very high pressure, then I need a very big compressor. Very high pressure, then I need a very high wellhead, very high pressure rating wellhead equipment, and so on, Then also the outside, the tubing collapse or tubing, something like that should be withstand all this type of pressure. For that reason, they are using the unloading valve. Then unloading valve, what we mean? I injecting gas, and I will show you this is unloading technique for that wells. The first valve is open, then they lifted the amount of fluid from here to the surface. This amount of fluid will be, only about two-phase flow, then reducing the hydrostatic head. When reducing the hydrostatic head and the second valve is open, the first valve is closed, and reducing this hydrostatic head after the gas is injected and so on. There is some slide later on, we'll go through this in details and so on. There is different type of valves in the market? Yes, there is different type of valve, but there is a main common technique, main common valves using in the market. There is some smart valve and some other technique of valves and so on and so on. The most common valve, the first valve is called, injection pressure operating valve. IPO, injection pressure operating valve, is respond to injection gas pressure. That's mean, this valve is open or closed based on the pressure outside the injected gas in the annulus, pressure of the injecting gas of the annulus at the valve depth. The second valve is called production pressure operating valve, PPO. Production pressure operating valve is respond to flowing pressure based on the flowing pressure inside the tubing at the valve depth. This is, just a schematical about how this injection IPO valve is working. This is simulated to the flowing, and this is a valve mechanism, how the valve, if the injecting gas comes here, and this is a payload under the valve, is presetted in the workshop with a certain volume, certain pressure of nitrogen, whatever, then it will be under pressure. If there is no pressure from outside, this pressure is pushed this port, and this port in the bottom will be closed. And when the gas, the pressure outside this gas, this gas lift valve reach to a certain value, is higher than the pressure inside the payload, is lifting this port is open, and then you allow the flow to go and so on. This just, I keep this for you just to understand, how this valve is working, what the difference between this one, and so on. I said, the second part in downhole equipment or the gas lift equipment is the mandrel. Mandrel in which the valve I installed. I installed this is valve and mandrel. Then the valve installed inside the mandrel. Generally speaking, in the market, there is two types of mandrels. Like there is different type of valves, but mainly there is two types of mandrel. One we called conventional mandrels, and the other one called, retrievable wireline mandrel. Conventional mandrel, that means the valve installed in the mandrel, but it's not from inside the tubing. The valve installed in the mandrel before I run the mandrel in the wells, before I run the completion in the wells. And usually this type of mandrel used for shallow wells and so on. It's not expensive, but it's not economical at the operation point of view. Because in case I have some problem with the valve, I need to change the valve for some operation, and so I have to pull the completion completely to retrieve the valve and change the valve. The main common one is what we call, it is retrievable or side bucket mandrel, conventional pressure valve or retrievable side bucket mandrel. In this one, you are connecting to the tubing, and you have a certain configurations, while the valve is installed inside the mandrel, inside the tubing. In case if I want just to retrieve the mandrel with a slick line, I run here, catch the valve, retrieve the valve, make repair, replacement, whatever, and rerun again, and so on. This is one of the main common valves, main common mandrel used in the market. Let us to back up again about, the unloading sequence, how to unload the wells. I think unload the wells, that's mean when the well have a completely full with the liquids. Completely full with the liquids, then in this case, we are running the gas lift, different gas lift mandrel in order to reduce the amount of flow, the pressure of gas need to inject it, and you restore the well to production. After well is completed, usually, as I mentioned before, you have some certain flow inside the tubing and inside the casing. The gas lift pressure, it's have a certain availability in the field. Maybe in most cases, not generally enough, not high enough to lift all the hydrostatic head inside the well. If I have a well, for example, with a depth 6,000 feet and the flow gradient 0.3 is up more than 2,000 psi, something like that, then you need to inject gas with more than 2,000 psi. What if you have a well at 9,000 feet or 10,000 feet or 8,000 feet? What if you have not oil? I have a water with a flow gradient 0.45, saline waters or something like that. Then you need 4,000, 5,000 psi. That's usually is not available or required a very high compressor and just to do that. In this case, a series of unloading the well to reducing, amount of pressure or value of pressure required to unload the wells using a different valves at a different depths inside the well. And this is one of the main important design steps in design when we design the gas lift, how to design the valve spacing, valve place inside the well in this case. Okay, in this case, the valve is designed just to use what's available of gas. Based on my availability of gas and the pressure of gas, I do the design and I spacing the valve inside the wells. This is just a first graph, talking from some Schlumberger presentations. These graphs, showing for the left side one well is full with the liquids, casing and tubing, If you look to that liquids, the pressure at the bottom against this liquid, this is what we call shut-in bottom hole pressure in this one, Then the pressure in the casing and the pressure in the tubing is almost the same. The gradient in the casing is the same pressure of the gradient of the tubing. The top one is the casing pressure, the bottom one here, is the gradient, is the tubing, the pressure of the fluid inside the tube. And this is, the required wellhead pressure to give the fluid to move to the surface. What's mean of unloading? How to unload? How to reduce? If I want just to lift all that fluid, then I need pressure at the surface equal to 7,000 psi. Because the annulus will be full of gas, the tubing will be full of liquids. And in order for that gas to push the liquid, the gas density is very, very low, Then all that should be full of gas. Then the pressure here should be equal the hydrostatic head of the pressure inside the tubing. Then if I need just, there is one valve and I need just to lift this fluid, then I need a pressure at least 7,000 psi to lift that one. But generally 7,000 is very high. Then for that reason, we use more than one valve to unloading the well. How that can be reduced the amount of wellhead pressure? When we start to inject gas in the casing, what happened here? Yes, in this case, in order to reach that, still the pressure at the bottom is the same, pressure between here and there is the same, but we're compensating, the equivalent pressure of this liquid inside the tubing in the annulus with the gas. Then the wellhead pressures of the gas, the injecting gas here, reach to more than 1,000 psi. Then I have to have more than 1,000 psi just to push this amount of fluids, inside the tubing and so on. Then I still above the first valve. There is no gas entering to the tubing. When I start to increase the gas, increase the pressure, and when I reach to around 2,000 psi, I reach it with the gas to the first valves. When the gas reached to the first valve, what happened here, When the gas reached to the first valve, the valve is open. When the valve is open, it allows the gas to enter inside the tubing. When the gas enter inside the tubing, is mixed with the fluid. When the gas is mixed with the fluid, then the average gradient of the fluid from the depths of the first valve up to the top is less than the dead oil. This will be low. Then if you look to this blue curve you found here, the gradient start to be decreased, Then the pressure here, if you look to the pressure, is moved a little bit, because the hydrostatic head here is equal only the head of the liquid, this only liquid, plus the head of the two-phase flow in this one. Then the equivalent pressure is less than the bottom hole now than 7,000 psi. If I start to continue inject gas, yes, I start to continue inject gas. In this case, I increase the gas pressure, and in this case until I reach it to the second valve. When I reach to the second valve, what happened here? Yes, the pressure reached the second valve is open, then allow gas to enter inside the tubing. Then the head of the fluids from the second valve up to the surface will be two-phase flow. The gradient for sure will be less than the dead liquid. Then the pressure at the bottom of the wells start to be creating some drawdown, some pressure less than the formation pressure. This allows the formation to produce some two-phase flow, because the fluid in the formation is oil and gas. Start to produce some fluid enter inside the well because the pressure is decreased, and meanwhile, I still continues to inject. I still continues to inject and so on until, all that downhole pressure is increased to the pressure I already decide or already designed before. When I reach to a certain amount or a certain depths, in this case, I consider this like an operating valve, and the well start to be reduced. This is the ideals. Instead to need, remember at the beginning I said, in order to keep this well flowing and lift the fluid inside the well, I need almost 6 or 7,000 psi. Now I need only 2,000 psi. See how much saving in pressure at the surface when I'm using more than one valve inside the wells. This just, some graphism, not our talking now. Okay, in order to design the gas lift or gas lift valve or type of artificial lift system, for sure, you need to have more information. Remember yesterday, I said when you're selecting artificial lift, you need to consider all the aspects in the wells, all the aspects on the reservoir, in the wellhead facilities, in all the criteria of the fluids and so on, Then for design of continuous gas lift, we need as much as information you put in front of you, your output design will be, will be more efficient and more good design. I need to know what size of tubing inside the well in order to know what the two-phase flow pressure loss will be inside, what size of material I have to run, what size of valve I have to run, size of casings in the annulus between casing and tubing and so on, depths to the center of perforation. What's the depth of perforation? Because in this case, this is what you call this a flowing wells, extension of flowing wells, and I need to have to know very well what is the bottom hole flow pressure, what is the oil API, and consequently the gravity and viscosity and so on. What's the formation gas oil ratio? Because I will injecting gas. What volume of gas I need to inject? And I need to inject volume of gas depend on how much even the formation assist me or help me, because I assist the formation or I help the gas formation. I increase, for example, if oil produced with gas oil ratio, for example, 1,500 standard cubic feet per day, if I start to inject gas, some volume of gas, and I reach to 700 standard cubic feet per day, then I increase the gas oil ratio, increase the gas oil ratio, I decreasing, the hydrostatic head and so on, specific gravity of the formation gas and so on, what is the required production, if there is a water, what water I have, what specific gravity of water, because I will lift that water, against how much wellhead pressure I will have to design my gas lift valve. Since I running or just I dealing or I working with the gas, then the gas is sensitive to pressure and temperatures. Remember the gas law, there is two main terms, gas law, pressure and temperatures for the gas. Pressure and temperature affecting with each other on the gas, Injecting gas pressure available if there is a wells, if there is a gas field near me, or there is a compressor, what size of compressor, if a new compressor or just a compressor already in the field, I have to rerun new wells and so on, Volume of gas availability and so on, bottom hole pressure, productivity index, type of reservoir, and so on, is the minimum information I have to have when I start to design some gas lift information. Gas lift design, there is different way, different methods used. Really, there is a lot of what we call software in the markets, Software, there is some commercial software, general softwares, and it's very efficient software, and some also private software, some, in-house built-in software, A lot of major service company have their own software to design the gas lift valve. And usually, most of the different methods incorporate different design philosophy based on what philosophy you have, based on what type of valve I have. Remember, I said I have injection pressure operating valve or a pressure or a production pressure operating valve. What type of valve I have, what type of well I have, what type of correlation, because sometimes due to change in fluid parameters and fluid concentration, water, and so, and maybe they required some correlation to correlate what is the two-phase flow inside the tubing, maybe change it with time and so on. Then, as I said, especially for gas lift, you have to simulate what you call nodal analysis. What type of fluid, what restriction, where is I need to reduce the restricted pressure and so on. And sometimes, we are used manual design. It's not efficient. Sometimes used for very shallow, for a small well, but for critical wells, no, computer assist methods program like Prosper, PipeSim, and so on. There is a lot of software using in the market. I will just, since most of you just are student, I give you just a very quick hint about the manual methods and how they are designed, while the software depend on that. Usually for the manual method design of gas lift, I have, I need to design the gas lift like this is the left side. How many valve I have to run in the well? At what depths each valve will be, the first valve, second valve, third valve. What's the space between first valve and second valve? For each well is a unique, each well have a unique design, unique system, depend on a lot of value, all the information I presented in my previous slides and so on. You need to start with a graph like this. You have some piece of papers. In the top one, you are representing, or just have a line to represent the pressures, and in the vertical one you need to have the line represent to the depths, and at the bottom you need to have at what depths of my perforation, what depths of the last valve I have not to run below in this one. Then you have a sheet of gas lift graph, what you call this a gas lift graph, up to these two axes, horizontal and vertical axis, and so on. First thing on this graph, you have to, to construct, or just to determine what gas availability, what gas pressures available, because based on my availability, I just design the system, design the valve space based on availability of the gas pressure and volume. But here, let us to consider what's the pressure gas, what is the injecting gas pressure at the surface, what will be the injection gas pressure at the depths, due to change in pressure, change in temperatures, gas gravity, not big difference, but you construct a line like this one, this can be determined from simulations run if you want to or just, empirical charts. There is some empirical chart depending on gas gravity, gas properties, temperatures, and so on. And there's some simple equations can be used. Then based on the available, what the maximum pressure will be at the surface, and corresponding will be how much the pressure if injecting downhole. This is represent the line injecting pressure gas. You can use some very simple rule of thumb like this one, pressure at depths, so pressure at surface, and multiply 2.3 for pressure at surface over 100 fill depths at which you need to calculate the pressure of gas over 1,000 feet. This is a very simple, roughly calculations, because, you need to have some, information about temperatures and some effect of temperatures and so on, Okay. Then I have this and construct this line. Second line, I need to have this, what type of fluid inside the well. Is the water, is the oil, what type of gravity of this one, Then I need to draw a line from the upper left corners, from zero, here upper left corner of the gas lift paper, representing the static fluid gradient inside the well. While the static fluid gradient is a very simple technique, equals the fluid gradient, multiply the depths, and so on. Then you have second line. Now we have two lines. Line represents the gas I will inject it. Line represents the fluid in the wells. What type of fluid in the wells? In the well, yes. What type of dead fluid in the well? What you call static gradient in the well. Then when I start to do that, I need to also to know previously what will be the gas liquid ratio, unloading gas liquid ratio I have to use. Available, it should be equal available injecting gas plus divided by the desired production rate. You know, I have a gas and I have a production rate. I have to lift it from this well. This is what we call, you know, how much amount of gas I need to inject it, how much amount of gas I have to, you know, to design to lift it this flow. You have to note that, you know, you are lifting a dead columns from this well and no gas inside this well. And then, for example, if I want to just, you know, to produce or just lift 600 barrel a day from the certain well, and all the available of gas, what we have gas rates from the compressor as a well sites, in it's 1,200 MCF per day, you know. Then the injected gas liquid ratio is divided by these two is equal to 2,000 standard cubic feet per barrels. How to do that, how to help, how to allow that, you know, it's usually you have two-phase flow correlations like this. This can help you or can support you. And in this one, you know, and you need to select what is the proper, what is the suitable two-phase flow correlation, flow gradients curve, you know, I have to use. This depend on what? Depend on a lot of information. For example, what tubing size inside the well? Because each curve represents a certain tubing size. Each curve represents how much fluid I have to read. This is 600, then I have to select this chart for 600 barrel per day wells. What API gradient fluids, what were API, oil API for that fluid I have to lift. For example, this one is represent 35 API. What's the gas specific gravity? I injecting gas. For sure, each gas has a certain specific gravity. What's the specific gravity of that gas? What is the average flowing temperatures? As I said, you know, temperatures have a very big effect on the gas. You start to look to what's the suitable two-phase flow correlations or just flow graphs, the gradient that exists, and you select this one. These are the first steps after the second, after the previous slides I have to do. For example, this one, you know, as I said, you know, each curve represents sometimes a certain correlation at a certain gas liquid ratio and so on. Then I represent, usually I construct this gas lift, this is gas pressure line, and this is hydrostatic line. Based on the previous curve, I select, yes, how much my gas liquid ratio. For example, if it is 600 as the previous design, and this is the situation of the well fluid, well completion I found in the well, I produce 600 barrel per day with 278-inch tubing and so. Then I select this curve. You see that curve at 600 barrel per day, and I took this curve exactly and I put it, you know, in the same chart. But at what, you know, it's not starting from zero, it's starting from the well head pressure. I stopped at the well head pressures, you know, and I overlay the gas papers, this gas lift paper on the curve, and I track the curve represents the calculated unloading gas liquid ratio. Then I have 3 lines on this curve like this, you know. 3 lines let us to say how we select the first valve, second valve, third valve based on this 3 lines. If we are using triangle and constructing a line parallel, you know, this line parallel to the static gradient of that flow, this dash line, you know, and we moved that line until it's reached to the well head pressures in the line from the well head pressure until, you know, that's, you know, this line is construct, you know, or just interact with the gas pressure line. Then in this case, you know, you have construct a line parallel to static gradient starting from wellhead pressure at 0 depth at the surface to the point, to what point? To the point where it's intersect with the casing gas pressure. This line, you know, this solid line until it's reached here. This theoretically should be the depths of the first valve. But due to downhole, sometimes it changes downhole. We don't know exactly, the pressure, temperature, what can be effect, efficiency. We take some safety factors. Safety factors depend on the type of valves, the type of gas, the type of wells, a lot of things. But in general, the people is sometimes people, according to some situation is using, if you don't know, you are using 30 psi safety factor instead to install the valve. For example, at depths 4,000 feet, no, I left this to the top little bit until the difference between the pressure of the gas and the curve represent the two-phase flow pressure is the difference between the two is around 30 psi. In this case, I draw a horizontal line until to reach to the depth line, and this represents the first valve depths of the first valve. Okay, this is same technique used for the second valve, but I have to remember that this valve now is working with a pressure not at the surface temperature, with the temperatures at the temperature, not with the surface temperature. Then I have to know what the temperatures at the wells. Then I have to also draw the temperature gradient curve in order to know, for example, the first valve is working at 100 degrees Fahrenheit. Then when I have to preset the valve pressure at my workshop, the pressure inside the valve, I have to consider these pressures should be open and close at this type of pressures, this type of temperatures, and so on. Because if I ignore that, then the condition of the pressure will be changed because the valves will be full with the gas and so on. With the same technique, you are going to determine second valve, third valve, fourth valve until you reach to the bottom. However, this is manual and not many people is using. Just this is, we are educating the student, just in order to understand the software and so on, how to have. But however, there is, as I said, there is plenty of softwares, and software will guide you, through each point you have to consider, in the design. He will ask you about what type of valves, who's manufacturing this valve, what size of valves, what, the total depths you have in the wells, what the production required, and so on. And this is a screen what inside you, some input data and output data from one of the measure using one of the common used software like PipeSim and so on, and at the final, he generates something like what we are doing by your hand, but is more accurate, taking into consideration all the factor while you are not able to taking by using a hand calculation. At the end, after you design these valves and place of the valve, you have to generate a table like that. Because each valve, this valve number 1, valve number 2, 3, 4, each valve should be working what the depth of the valve, what is, the temperature of the valve, what the working pressure should be as the valve open and close, and so on, This is just, the valves and design of the valve. I like you to remember, since you are working with artificial lift, for each type of artificial lift in the market, there is an API and ISO standards, can guide you and control the manufacturing, the design, guide you for design, and so on, This slide just show you some of the main common list of API and ISO standards used for gas lift system, If you are click on in each one of that, will open for you, for example, API specification 11 VB, it's a gas lift valve, orifice, and dummies. It gives you all the specs about the gas lift valve, the size, what's inside, and in what size of mandrel you have to run, and so on, you have, for example, you have one like RP 11 VB is recommended practical for gas lift system design. The one before the last one, is recommended practical for gas lift system design and performance prediction. Yes, how to design gas lift is just guideline you. For sure, there is some assumption in these wells and so on. It's not like the software, but this can guide you about how to design and so. There's several difference you can reference you can look for about gas lift and gas lift system design, operations, and so on. This is just a very basic information about gas lift, how the gas lift is working, and how the gas lift is design, what the main equipment is. The gas lift is a big subject, but this is just the first step in order to to understand and to learn about gas lift. Thank you, and this is just all
Thank
what we
you.
have
Thank you
about
so
the.
much, Dr. Mohammed. It was really, really
Good.
informative. Thank you for your time and
Thank you.
effort. We just
Thank
have
you.
a few questions. The first question, can we use gas lift in high viscous fluid?
It's not recommended, It's not recommended because, for high viscous fluid, you are injecting gas, and the gas going to, should be mixed with that fluid. If the fluid is very high viscous, then the gas will slip from the fluid. If you look, when you start to, to design or just to study two-phase vertical flow correlation, there is some, some terminology called slipped and hold up and so on. And usually is not recommended. This is the last choice to use gas lift for high viscous fluid.
Okay, and
Okay.
the second question, if the well's productivity is very low until a point in which the surface line of the formation fluid, gas and oil, is below the packer, is gas lift is efficient in this type of cases?
No, no, because gas lift, simulated fluids, and gas lift he have to lift the fluids on side of the well. In this case, if there is a gas enough gas in the formation and the fluid is not viscous fluids and so on, maybe, and not deep well, and also not deep wells, maybe sometimes the intermediate gas lift can, but this requires to look to the properties of the fluid, the downhole pressures, the depths of the wells, and how much pressure I need to have, because but for sure will not be efficient, and sometimes maybe we used by, as I said, with some combination, if the gas liquid ratio is high enough, what is a produced gas liquid ratio to a certain value, there is a technique maybe in the lecture number 4, or later on we can present it, what you call gas lift assist plunger lift system, but it's not recommended,
Okay. The last question, is it possible that after designing a gas lift valve depth, the liquid level falls below it?
Yes, it's possible because the well, if you are running with a depletion drive reservoir, for that reason I said, if you remember, I have different valves in the wells, and the gas lift system is a flexible. When we design, I have to consider this is reservoir is a depletion drive reservoir. With the time the bottom hole flow pressure or reservoir pressure is depleted, then when I design the valve, I have to consider not to operate with the last valve. Maybe I can keep one valves or two valves, as a spare, to do that. But it's sensitive to the bottom hole pressure for sure, yes.
Okay, thank you so much, Dr. Mohamed Ghareeb, and thank you all for attending, highlighting that this session would be recorded and uploaded soon on PioPetro YouTube channel, so make sure to subscribe on our YouTube channel. Thank you so much all, and bye.